All right. Hello, everyone. Um, Today, I'd like to talk a little bit about a project I've been working on for the last few months that I'm really excited about. This was part of my GSA presentation in 2022, um, but I also wanted to record a version for YouTube for anyone who wasn't able to attend the meeting. So today, I'll be talking about the role of fractional vaporization as an igneous differentiation process during the formation of rocky planetary bodies. So when we think about magmatic differentiation, we're trying to describe how an igneous rock forms from a common parental magma. And there are a lot of processes that are typically associated with this crystallization process of igneous rocks. And those processes are, some are more familiar than others. Like there's magma mixing, there's liquid immiscibility, fractional crystallization. But for the last few months, I've been focusing on another process that I think might be relevant um, with regard to the liquid composition, and that's vaporization. You can imagine that as volatile and moderately volatile elements leave the liquid and enter the vapor phase, it's going to change the composition of the liquid and potentially affect the crystallization sequence of that liquid. And so there's been quite a bit of previous work done on the vaporization of natural systems, pretty much inspired by samples returned during the Apollo missions. These samples were found to be devoid of many volatile and even some moderately volatile elements. And so there were a slew of early experiments done on both minerals and glasses to try to get an idea of how vaporization happens with natural compositions. And then these results were turned into thermodynamic models that represent both equilibrium and fractional vaporization. And the current sort of place where vaporization has really been being used in the modern literature is in the study of early atmospheres or current atmospheres on exoplanets, where there's maybe a magma ocean generating a atmosphere with moderately volatile elements. And then there's also people interested in planetary differentiation, and they start with sort of a already vaporized initial composition and then look and see how magma oceans crystallize. I'm kind of interested sort of in the in-between here, before vaporization is finished, so it's still ongoing, but more focused on the magma ocean and less so on the atmosphere. And so there's been some recent work that has demonstrated that vaporization may have occurred for hundreds of years during the crystallization of the lunar crust. This figure from Saxena et al. 2017 shows that the near side, so everything left about here, there was vaporization occurring for almost 430 years on the near side, and deposition on the far side of the moon, which is a whole other topic to talk about. And there was an idea proposed by O'Hara and Yu in 2015 that suggests that vaporization could have perhaps promoted plagioclase crystallization in the lunar magma ocean and helped form the lunar crust. And so, there's also evidence of vaporization being useful in sort of the material science industry, where they have what they call the flux method, where they can take a crystal of a certain composition, artificially lower its melting point using a volatile flux, and then drive that flux away through evaporation to force crystallization of pure mineral or crystal phases. So for instance, there's cobalt manganese oxides that uses a very volatile lead fluorine flux, but there's also some more geologic and planetary realistic compositions like sodium silicates and pure silicon that use a sodium flux, and that's what I'll be focusing on today. And so our primary driving research questions is the flux method relevant to natural systems? And can vaporization affect magmatic differentiation of maybe magma oceans? And so to answer these questions, or attempt to answer these questions, we've been doing a series of high temperature experiments in the albite anorthite binary system, where we choose a starting glass composition. We try to vaporize sodium and drive the composition into the subliquidus and even subsolidus phase on this particular phase diagram. We chose this system because sodium oxide volatilizes at relatively low temperatures, and calcium and oxide and aluminum oxide are much more refractory. So any vaporization should be limited to the sodium. And plus, since we're interested in sort of how the anorthosite crust on the moon formed, this could potentially provide some experimental support for that hypothesis. And so to do our high temperature experiments, this is the apparatus we use. It's got a 400 watt CO2 laser in the back that can then pass a laser up through this barrel and focus it on a sample that's found in a conical nozzle. That conical nozzle can pass gas over the sphere, levitating it. And so this is a fully containerless method. And then the laser can heat that sample up to temperatures greater than 2000 C. And we can record the temperature using this infrared pyrometer and this visible light camera. So the first step in our procedure is to take our starting composition as a mixture of high purity reagents. We can fuse spheroids using those powders, and then we can homogenize those spheroids by loading it into the sample chamber, levitating it, and then heating it up. And so the purpose of this stage is to make sure that we remove all the bubbles, we remove any relic crystals, we make sure it's a homogeneous glass through and throughout, the composition is uniform throughout the whole sphere, and then we can quench it and do our vaporization experiments. So here's an example of a successful vaporization experiment where we've seen evidence of vaporization at high temperature, driving the composition hopefully towards the anorthite end member on our phase diagram. And then we watch for crystallization behaviors. And so if we pay attention to these flashes of light that you can see near the surface and maybe a little bit on the interior of the sphere that move, we think these represent crystallization fronts as the sphere begins to crystallize. And so we can do some starting assessment to see if vaporization was successful. The easiest thing to record is mass loss as a function of total laser energy. So that's the amount of laser energy that the sample is exposed to. And we can see that as laser energy increases, mass loss also increases, suggesting we are losing material to vaporization. We can also use our EDS detectors to estimate the sodium loss as a function of laser energy. And sure enough, we see from sort of our starting composition, and as increasing laser energy, or as laser energy increases, so does our relative sodium composition. We can also look for textures in our samples. So on the left here, I have a backscatter electron image of AB8020, which is sort of a pure starting material, fully homogenized, and you can see it's primarily a glassy texture with a couple of vesicles, but generally very glassy. And then we can compare that to sample AB8018, which is the sample that I showed you in that video that looked like it was crystallizing. And sure enough, we can see these sort of spin effects, sort of radiating crystalline textures. And if we zoom in closer, we can see crystalline textures next to sort of a pot-marked glassy phase. Okay, and then we can turn on our EDS detectors and we can look for the elements in both phases, in both glasses, and see if there's any evidence of vaporization. So the green line here on our X-ray spectrum is from AB8020, and we can see all the elements we'd expect for an albite composition. We've got oxygen, sodium, aluminum, silicon, and calcium, right? But if we look at the sort of maroon and blue or purple curves, those represent the crystal and glass phases from AB18, and suddenly we see no sodium and no silicon. We weren't quite expecting to lose silicon, but it is a moderately volatile element, and it's possible that it could vaporize under the right conditions. That leads us to conclude that the crystal phase is actually a calcium aluminate and not actually anorthite, and we're still trying to figure out exactly why that might be. So why didn't more spheres crystallize? Of the samples we've done experiments on so far, only one successfully crystallized, and that's despite the fact that many of them, the amount of sodium loss actually pushed the sample into the subliquidus or even the subsolidus phase at an average temperature of the experiment. And we think this is primarily due to kinetics. This composition or similar composition was actually explored by Scherer Bowen in one of their papers, and their samples were held at like 1100 degrees for up to 5 years, and they showed no signs of crystallization, suggesting that maybe our experimental timescales are just too short to promote crystallization. And it's probably because this is also a polymerized melt, and polymerized melts typically have a harder time crystallizing than depolymerized melts. The other possibility is that we don't have any nucleation sites because we fully homogenize our spheres before our experiments. And so for future experiments, we're going to try to find maybe a more depolymerized system like the forced radensitite quartz system, or we'll try to seed experiments to promote heterogeneous crystallization using some sort of inert phase that won't interact with our melt composition. So why are we interested in doing these experiments? Well, we want to find out what the effects of vaporization on magma oceans are. And to do that, we did some modeling. We took a generic magma ocean starting composition. We performed some fractional vaporization calculations using the magma code from Fegley and Cameron. And then we took partially vaporized compositions and used them as inputs into melts to try to see if there's any change in the liquid line of descent as a function of vaporization. And what we found is that if we don't vaporize our initial composition, our crystallization sequence starts off as pure liquid. Then we enter the liquid plus olivine phase. Then we add OPX, so it's liquid plus olivine plus OPX. And then after about 70% of our liquid has crystallized, we get plagioclase. But if we look at 25% vaporization, we see some differences. We start with liquid, go liquid plus olivine, and then right about after 60% of the liquid has crystallized, we find liquid plus olivine plus plagioclase. Plagioclase effectively leapfrogged OPX in the crystallization sequence. Also, if we look at the total modal abundance of plagioclase from 0% to 25%, we see a 48% relative increase in the modal abundance of plagioclase, which is not insignificant. We also see changes to the physical properties of the melt. So as we vaporize on the X here, we can see increasing liquidus temperatures of the melt composition and also an increase in the plagioclase onset temperature. And that's important because both of those things would cause plagioclase and the magma ocean to crystallize sooner in its cooling history. We also see a relative decrease in the density of the liquid, suggesting that maybe as the surface of the magma ocean begins to volatilize, the composition of that melt becomes less dense, and that would encourage that layer of melt to stay close to the surface of the magma ocean, promoting either more vaporization or even more crystallization. So some quick conclusions regarding this study. We believe we've demonstrated that vaporization can modify the composition of a melt at temperatures associated with planetary processes and natural systems, and that changing composition can affect the crystallization sequence of that melt.